potential is just unbelievable if we pull this off, and we will pull this off, and that's the dream, and we actually have to pull it off. It's almost, I think we're at a point where this is a responsibility. We can't know what we know now and not do something about it.
I agree.
The sky's the limit and space is the place.
And I think it'll make the biggest difference for humanity, honestly. Whether or not we'd finish before we die, this is the project to be participating in, because when it is accomplished, I think it's the thing that will monumentally change the experience of humanity more than anything else.
Lay the foundation strong, and if others finish it, cool.
Yep. I planned a little start over from the beginning and tell the whole story again, because it's good practice, but also I think it helps to connect the dots each time in a different way. We went over it a little bit already, but we want to open with stating what goal we're aiming for right now. Echelon and I actually have a pretty far-reaching timeline that might take 10,000 years to accomplish all the things that we're really interested in. But the biggest first outstanding point that I'll put here on the timeline for us now is creating the universal replicator. Okay, it doesn't exist right now. It's more of a Star Trek fantasy idea. Not exactly the way Star Trek meant it, but the output would be basically the same. So we're looking for a way to make universal replication. Meaning we need a universal base logical system that can be converted into every other stable configuration representing everything in the physical world. So we want to have basically like a replicator in Star Trek, where you can go to your machine and output the material you want by putting some sort of material in, and it can convert the state. Star Trek does it, I think, a little bit differently, where they imagine all the atoms are pre-sorted. Then you call what you want, and it puts the atoms together. It's a lot more work, really. We're just starting with a state and transforming the arrangement in that state, which is a lot less work than starting from completely separated and put together. However, we're also interested in understanding all the possible stable transition states and what the transforms or actions that occur between transitions, so that we know all the possible functions or actions that are available to be taken advantage of naturally, right? We want to know how all the inner gears are working within the system that we're interested in, which the system we're interested in is the physical realm, right? The domain of physics, the properties and parameters reported measurement-wise in physics about what our world actually is. So that's our goal. However long, even if it's a 10,000 year out goal, we're aiming towards that goal, okay? And if it takes longer than our life, hopefully people continue it after us. But we have a feeling already it might happen during our life. We have a feeling that we might be getting there and making a lot of progress. So our secondary goal with this talk is to help see the steps that we're taking towards that, so that everyone can try to get on the same page, but also then to develop the method by which we're taking those steps, right? So we want to put out as much information as possible here in one big swoop. But first we need to contextualize the information so it feels as important as it really is. So we can give a little history in the background, right? So the history of science. At what point does somebody who's asking questions and investigating the world become a scientist? What's the skill that you would say is needed in order to be a scientist?
Coherent measurement.
You need to be employing measurements for your investigations, not just guessing. Curiosity is necessary to even just, it's almost like a consciousness necessity, right? But you can't call someone, you can call a cat very curious, right? But you can't really call them much of a scientist unless they use measurements to decide to learn this, to investigate from one story and jump to, no, this makes more sense according to the measurements. Implementing strategy. So logically organizing information, right? Arranging things so that they can be organized and compared. Yeah, great. So these are all skills that help science. Then we have the whole scientific formal method where we use a hypothesis, right? Good. So in history, when did we start measuring things?
Well, we measured in the Babylonians, they had weights and measures for product exchange.
Yeah, so it's a little vague when I say it like that. So if I say that, you say, well, I can't imagine a human who never measured anything. I mean, in a way, we've always measured. How much does this weigh? Maybe you didn't measure it by writing down a number, but you vaguely measured it, right? I mean, systematically, very clearly measured it, such in a way that you can associate a number with it, right? This is an interesting thing. With measurement, you need numbers.
The Mesopotamians, they had measurements in currency and all those kinds of things. And so basically, they invented writing, and so the writing would also
a necessary ingredient. If you're going to need to be writing down numbers to report a measurement, then writing is also a necessary ingredient for science, right? When you get to be the level of a scientist, it means you're somebody who has recognized the value of systematically looking into the world and trying to keep track. In fact, trying to keep track far better than you can just in your own head. Keep using tools like whiteboards or paper and writing them down as you go, because you recognize that you forget when you're 12 digits in, you're like, oh, I forgot already, I have to start over. So recognizing that your brain can't keep track of certain things so well, you take advantage of other tools that get past that, like writing. Is absolutely necessary, but it's also absolutely necessary to be thinking. Now, let me try to be as clear as I can about that. I'm not saying there are no thoughts going on in your head if you're not writing things down. I'm saying you're not developing those thoughts. They're not evolving. Right? Writing is literally a tool that's necessary because of how our brains work to get past the fact that you keep getting distracted, past the fact that you can't remember the next number, right? It gets you past these little glitches and helps you look into the world more systematically. Beautiful. Writing, measurement, and numbers are all critical. Well, here's another step, systematization with those numbers. It turns out that you could use any base as a measure, meaning, you know how we use carats for diamonds? Do you know where that comes from? In Greece and surrounding areas, they have a carob tree, and the seed of the carob tree is very, very uniform, and it weighs what we now call a carat. So they would pull off the seeds and use the number of those to give a systematic, now they're not exactly the same, but as far as a thing that produces things in nature, you can go collect a bunch of those and they're pretty much uniform. So it's a way to then measure more accurately. Becoming more systematic is extremely important, because if you're measuring with the length of your foot as the base, and I'm measuring with the length of my foot as the base, and they're very close or they could be very different, we'd still be looking into the world with systematizations that didn't cross over so well. So having other people look with you means you need to figure out, we need a general set of systems that we're all agreeing on if we want to use your data and my data and so on, right? Okay, so measurement gets bigger now. Measurement allows us to be looking into the world as groups. That's interesting. I mean, in a way, we were looking at the world as groups before, but we group up in perspectives and ideologies and religions and cultures and stuff, almost in a way that keeps us trapped in that one perspective. We don't group up in a way that helps us evolve to the next perspective. We group up and coalesce when we're trapped in a perspective, right? How many kinds of things can you measure? How many kinds of bases are even available? And when I ask that, I actually want to get at the base of how many kinds of simple bases are available. So is there a root system to all the possible kinds of measures there are? There are hundreds of kinds of measurements you can make of things in the world. Okay, all of these things, it turns out, all the units for measurement can be reduced to only 5. Time, some base for time, some base for length, or I'll call space, charge, mass, and temperature. Okay. There are many bases you could pick randomly to associate to time and space and charge and mass and temperature. You can pick anything you want, standardize anything you want. But there are only 5 kinds of things you can measure. That's weird. Okay, I mean, that was surprising. Why is that surprising? Really, why is it surprising that there's only time, space, charge, mass, and temperature? Because when you look around, you see way more than 5 things, right? I mean, this is a really, really big thing to notice, that all the things that have ever been investigated or described or noticed so far by all the scientists that have ever lived, as far as we know, all those things are only making measurements in time, space, charge, mass, and temperature. Now, it might be charge cubed and space squared and time to the 4th involved, but they're only composed of these 5 kinds of measurements. Next big step is to discover that in physics there are equations that give us direct connections or conversions between things. I think all of us might remember some very famous ones, right? E equals mc squared, or force equals mass times acceleration, right? But there's a lot of equations in physics. Why is it not force equals 3.2 times mass times acceleration? Why is it exactly just mass and acceleration? Why isn't it just proportional to? Well, it is proportional to. If you didn't pick a system of units that is coherent to all 5 of these. In fact, this sentence right here, this logical sentence, is true when we pick the right system of units that connects these 5. Now let's pause there for a second. There is no sense to the word right system of units if you're only talking about one dimension, right? If you're measuring in seconds or in hours or in 3/4 seconds, you can, as long as you tell me what your base is, then report a number, I know what it means, okay? But to be forced to a specific base from these equations, you need to have more than one dimension involved. In fact, you're not actually forced all the way to the set we use until you use all of them. But when you do, we figure out there's a coherent system of units. And that coherent system of units says that there actually is a special base, a boundary and a cutoff written into the structure of nature. And we did not expect that. There's a cutoff here called the Planck time. I have a symbol T sub p. Okay, this is a scale 5 point something times 10 to the negative 44 seconds that defines the minimum cutoff for the measure of time. There is no coherent meaning to being able to measure time less than that. It's a cutoff written in to the thing we're measuring. It's a big clue. Now, what is that thing? Nobody knows. We didn't expect to even run into this. We didn't even ask for these, okay? They were big upsets. There's also the Planck length, the Planck charge. Where do these come from? How do we know that the limits are even there? All 5 of these just get, length L sub p. They're all sub p for Planck. These are just the limits in the measures available in reality. Now there's another separation here. 2 of them are different than the other 3. They're all, all 5 are different from each other, but these 2 represent limits that are minimums. These 3 represent limits that are maximums. Interesting, right? This is a minimum, this is a minimum, and then we have 3 maximums. All right, I should explicitly state, when we get to the coherent system of units, the one that these 5 boundaries applied to the equations of physics, there's a long list of equations of physics. When we arrange things according to these cutoffs, then the units we should now use are the newest definition for the second, the newest definition for the meter, the newest definition for coulombs, the newest definition for the kilograms, and temperature, which is Kelvin. What do I keep saying newest definition? Well, when we started out with our first definition, the second, it's not the definition we have now. We actually use the speed of light to define the second. We use the speed of light to define the meter. Okay? We're using the constants of nature to define the system of units that minimize the structure and pattern in the constants of nature or in the equations of physics. Great. So these units now, even though the meter started out at like 1 billionth the distance from Paris to the North Pole or something crazy like that, I can't remember, but it started out like that to be a practical measurement of unit and just to have a standardized one. It doesn't have that definition now in science. The definitions of the units in the coherent system of units come from the constants of nature that give us the cutoffs called the five-Planck constant. Okay, so in our investigation in the world, we've gotten from feeling the world out, playing in the sandbox, to realizing my brain's not doing it as well as I want, right? I've figured a lot out by playing in the sandbox and asking people things and looking with my own eyes and trying to guess. But if I use a ruler, I can actually figure out how far away things are systematically, and then I can find out whether or not I was guessing well. Right? So when we start using measures, and then the next step we start finding out, well, there's actually only 5 base kinds of measure in the world, then we can be really, really interested in why do those 5 measures, why do those 5 dimensions have limits? Why are they cut off? I want to give a little jaunt in pre-science history, some math history. The Platonic solids were famous, really famous early on. Why? What's the big deal with the Platonic solids?
There's only 5.
Yeah, the mysterious thing is only 5 of them, and it kind of makes you feel like, why? But what does it mean when we're saying there's only 5? What are Platonic solids? Geometric shapes of just faces, 2-dimensional faces, of all equal length sides. You pick side 1, pick your unit side length, but make it a 1. And now you can make it a triangle, or you can make it a 4-sided, but they all have to have the same length sides, and then you make a closed volume. You wrap a triangle with another triangle, all equal side, and see if you can close the volume. Well, the Platonic solids are the only shapes with all equal length side faces that can close. The only ones. You can't invent another one that fits the rules. And the fact that there are only 5 natural geometric shapes that can do something like that is almost the invite into math for a lot of people, right? It's like, what? Why would that be? There's 5 shapes that can do this? And what does that even mean? Then you start elevating the importance of these shapes and try to consider all their properties. Now, for a long time, staring at the Platonic shapes or having a model out of wood in front of you or something was almost akin to going to church, or in some cases exactly like going to church. It was what you would examine and try to get a message from. You would look at these things and try to figure out, have a sense. There's some more message here I'm missing. There's something more in these solids. Staring me in the face, I can kind of feel it, but I don't know where it is. For 2,000 years in our history, there were large numbers of people who treated the Platonic solids religiously, who were extremely interested in their features and expected to get new information by spending their time looking at them. And yet, for 2,000 years, not much new was discovered. And then Leonhard Euler comes along, all on his own, looks at the Platonic solids and decides, well, why don't I just systematically write down the properties of these objects? Why don't I be somebody who's a scientist, who's employing the skills of writing, right? So you don't forget, but also systemizations, you can compare directly, and just employ that to the Platonic solids that everybody else has been staring at for so long. Now, how do you do that? What features do these Platonic solids even have? They all have vertices, or the points where all the edges come together, right? They have edges, and they have faces. So no matter which shape of the 5 it is, they all have those things. So you can count up these things. But these features are actually, they have something interesting about them. How many dimensions is a vertex? 0, right? An edge is just a line segment. It's one-dimensional. And a face is 2-dimensional. It's an area. Huh? Yeah, then we also have a volume. And traditionally we'll call this a cell when we're talking in this conversation, right? And it's 3-dimensional. Okay, he looked at these objects that people have been looking at for a very long time and just decided to systematically count up the number of vertices, the number of edges, and the number of faces for each one, and write them down. And when he did, it became immediately obvious that for every single platonic solid, if you do the vertices, if you take the number of vertices it has, add them all up, write down the number, and you subtract the number of edges, and you add the number of faces. So let's restate that as, we take the number of zero-dimensional features minus the number of one-dimensional features plus the number of two-dimensional features, it always equals 2. And if it doesn't jump out why that's really exciting, just remember for 2,000 years people were having the sense that there's some more information buried into these 5 magical shapes, these 5 only shapes that can fit these rules. They were staring at it for a long time feeling there must be some other connection. And look, it only takes systematically paying attention to the details of the features themselves to find the connection or a connection. This actually leads to an entire field of explanation. It blows up from there, okay? This is a huge window. But until you look into things this way, it's just completely glazed over, right? There's no other way sometimes to see better into reality than to literally sit down, let everything else go away and say, all right, how many features are there? Let's just count them. Right? List them, compare them. This is how we look into the world. But sometimes it takes somebody to come along and just remind us how to do it correctly. We looked at the world in the sandbox way and got pretty good stories. But none of us had good stories about why, when you shoot an arrow, does it come back down? We all know it does. We get really good at playing against gravity. We develop our skills throughout life under the presumption and the familiarity of the presence of this force, but we don't measure it. Think of how many of us today could still say this. How many of us have spent our whole life investigating as we feel we are, right? But we don't stop to investigate things that we're curious about, like gravity, in a way that involves measurement. This is what I was trying to get at from the very beginning when I was saying, if you're not writing, you're not really thinking. You're not with the ing, you're just at the same think, right? You're not moving on with your thoughts. The same sort of thing. Galileo, first person in history that stopped to think, maybe I should just measure how things fall, and that'll help me understand why they fall. Now think about this. This is a step that's profound, just like this step is profound. Anyone can do it, but you have to think of it as an option. Anyone can measure dropping something if you have a measuring stick, right? And actually you need to be able to measure time too. But if you do have a weigh, a ruler, and a stopwatch, you can now measure the effects of gravity. And you can put them on a ramp to slow them down if your stopwatch isn't that accurate, right? You can do all kinds of things to start playing with gravity using measurement. And he did that. And because he was the first person to do that, this is a huge thing to think of. It wasn't because he was so much smarter than everyone else that he impacted history. It's because he thought of measuring something. And those measurements alone, taking them seriously, gave him insight into the world that people didn't have. That's what we call smart, but he got there. That evolution of thought, of character, came just because he realized systematic measurement was the way to get more insight. Okay. And he's probably everyone's, one of their heroes, because he came to the conclusion that gravity is geometric, right? He found the geometric code built into gravity. Every time we see things going like that, he found a way to characterize that it's geometrically bound. What does it mean to be a division algebra? And how many dimensions could you have a division algebra in? First question, to be a division algebra means if you have a number line, right, and you're representing, this is a one-dimensional number line, it has a 0 in the middle and a 1 and so on. The rules on this metric, this one-dimensional metric, can count as a division algebra. You can perform addition, add 1, add 1, add 1, and subtraction, subtract 1, subtract 1, subtract 1. You get back to where you were. You can perform invertible operations, so addition and subtraction are always invertible. You can get back to where you started by countering the operation you just did, okay? You can do multiplication. You can do division except for at the point of 0 in the middle. There's a, right? You can't divide by 0. But everywhere else you can. So there's these operators where there might be special points where you can't do an operation, but the general field you can. You can also have a division algebra in 2 dimensions, right? We're all very kind of familiar with this, the x and y. It works. The mathematical rules in 1 dimension also work just by extending into the presence of another dimension. You can have 2, and all the rules work this way and this way at the same time. Beautiful. Can you have a division algebra in 3 dimensions? What do you guys think? Yes? No? Yeah. And that's the intuition almost everybody has. Of course, why not? The world's 3-dimensional, you should. But Hamilton tried for years and years and years to find a way to make a formal division algebra that would work in 3 dimensions, and he couldn't, until he finally figured out, I need a 4th. And then it worked. So a quaternion division algebra, or what we call a complex division algebra, or real, which is 1-dimensional, okay? Quaternion means it's the 4-dimensional version, and that 4-dimensional version, now the rules do all work again, including division. And there's one more that's 8-dimensional, and we call it the octonions. So these are just algebraic systems, division algebras that you could employ that give the ability for reversible operations to be employed in that system, okay? There's 4 kinds, a 1-dimensional, 2-dimensional, a 4-dimensional, and an 8-dimensional one in math available, and that's it. If you go to the 16-dimensional version, you lose some of the abilities to do operations. You can keep doing some of them, so it's a partial division algebra, but it can't be a full division algebra at 16. Okay. That's a beautiful thing. It's been thought for a long time that that's going to ultimately connect to a theory of everything or fundamental things about number theory. Another one is calculus, and it's geometric interpretation. So there's 2 things in calculus I want to bring up. It's a beautiful trick, Newton and Leibniz, others. They became very interested in understanding graphs to a much deeper level than we had before. So when we pick graphs that are very easy to use geometric interpretations or our intuitions on, like straight line, it's pretty easy to then talk about picking some point out here and finding the area between the axis and under the curve. But when you have a graph that's not so simple, like that, and you want to ask questions like, how do I find the exact amount area underneath this curve from, say, here to here, pick some points, it's not as easy. Now let's stop for a second and think, what are we doing when we make a graph? We're scripting a relationship between 2 different dimensions. That's what we're doing. We've got x as a dimension, x as a dimension, we've got y as a dimension, and we have the relationship between x and y written down as the shape of the graph, right? Now, when you employ a graph to represent dimensions, it gives you insight to their relationship. So these are very, very useful things to get good at doing. But we didn't have a method early on for representing the amount of area, say, between here and there of any random smoothly connected graph. So what's Newton's insight? Well, we can't do it for shapes that we don't know well, but we can do it for some shapes we do know very well. Rectangles, that's pretty easy. So, for example, we could choose to slice up this whole thing, right, into equally spaced pieces, and we wouldn't think of it as giving us the area under the curve. Instead, we'd think of it as giving us an approximation to the area under the curve as we keep going. But then the trick is, all we have to do is make these things as skinny as we need to make our approximation as accurate as we need, right? And you're never going to need infinite accuracy, so this trick will allow you to eventually get close enough to the real area just by making the strips smaller and smaller. And with the advent of computers, that means more and more strips, but the computers are fine with working with more and more, right? At least up to certain limits. So this insight was beautiful. We could take something like the relationship written down between 2 dimensions, and we could strip it up. We could divide the whole thing up and add all the pieces to get the whole picture to put together. But we're stripping it up to make sense of it. Now, we usually traditionally take this as a limit to 0, and then we introduce, Newton introduced this confusing thing that's still kind of an upset in math that hasn't really been resolved. This infinitesimal notion was, it's a thing that's smaller than all other numbers, but not 0, so that you can divide by it. So that basically means you treat it like a 0 unless you're dividing, and then you don't. And everyone's kind of scratching their head about that. In fact, people were very back and forth with Newton about it himself, and he needed to employ it in order to make this work. Now, since then, we've kind of gotten other ways of addressing things that make that less of a problem. You can talk about calculus without having to go to the infinitesimal all the time, right? You can do it in terms of matrices. And with matrices, things like squaring to 0 become possible and easy to understand. But normally, if you say, what's the square root of 0? You'd think 0 is the only option. In matrices, it's not. There's an infinite number of options for the square root of 0. In general, we got two things that we're going to be doing. We're going to redo the entire formalism of calculus, right? And when we get to the infinitesimal, what we're going to do is we're going to have built-in actual bounds. We're going to have, when we strip things up in one of the dimensions, there's going to be a cutoff at the Planck mass. Okay, so there's a cutoff scale, which is around 10 to the negative 8 meters. So it's small. Our strips are going to be tiny, imperceptibly tiny. You wouldn't be able to see it with even a microscope. They're so small, okay? But they're not 0. And this other direction gets stripped up well, the size of the strips, the steps here, is bounded by the Planck charge, okay? And that's approximately 10 to the negative 18. Both of these strips are tiny, 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 okay, as we're dividing up the world in X and Y. But it's not 0 in both cases. And because of that, we actually get away from all the confusion of infinitesimal, but we make our connections be very explicitly vivid. We have an exact bound where this stripping up construction is occurring, and also where it ends. Past that, it's not occurring. Great. So calculus. Formally, the rules for how you can strip up determine the rules for then how you must fit together, right? It should be kind of intuitive. If there's a set rule for how you're going to be dividing things, and you need everything to stay bounded like a manifold or closed, so no gaps formed by that, then the stripping itself should code also how they're going to fit together, right? It's like the inverse of it. So how we divide things up defines differentiation, and how we then put those pieces together, each of the strips, put perfectly back together the rules of integration. So calculus itself reveals the rules of how nature's boundaries are being divided up and perfectly seamlessly smoothed together as they do, over and over and over. That's a really beautiful picture. What's the geometry of that? How do we have a geometric interpretation of what's going on? Well, the best we have is saying the object that obeys the rules of differentiation and integration is called the n-hypersphere, okay? The n-hypersphere naturally divides via integration and differentiation. So the picture you want to have in your head, if you want to be able to visualize the action of calculus, is the picture of the n-hypersphere. Now, in our model, that's incredibly exciting because we've also found from the constants of nature that it seems that the external projection of the minimum manifold is the n-hypersphere of maximal volume. So the built-in characteristics of calculus are automatically put there by the structure of the external projection. Okay, and it's simple as it can get, but really beautiful. That means when you get what's going on, you'll be visualizing just how the domain breaks up into a certain number of walls and boundaries and twists them perfectly together to make it so that there's no gaps in the process. You're going to have to zoom in and form an intuition for what it looks like down there. Okay. Now, general relativity. Okay. So Einstein comes along, a figure that everyone knows something about, and he spends his time trying to intuit his way to the truth, right? Like a lot of the people we might call heroes have. And what does he contribute? What new idea does Einstein come up with? Well, quite a lot of them. He tries to imagine what light is. He tries to get a visceral understanding of what gravity is. He came to the realization that even though we see in our first approach experience, a three-dimensional world around us, there's actually an encoded 4 dimensions. That time is balancing against the other 3, right? And it's part of the logic. It can't be extracted. He didn't just tell us that, hey, there's another dimension. He found the structure of the dimensions. He found that we live in hyperbolic space. 4-dimensional hyperbolic space, which means one of them is reversed. The time can be negative from the X, Y, and Z, right? In the signature. So he found that we're in a 4-dimensional structure. The world we live in, the world we try to make measurements in and stuff, is 4-dimensionally arranged. And that arrangement is very specifically geometrically hyperbolic. Those are all monumental changes of perspective that we didn't have before. One, the whole systematic process of getting to the coherent system of units, that one took up until basically now, right? That was a slow-going one. Einstein's insights were much older than even people being familiar with a coherent system of units. But his insights actually, if you were to blame anyone, we'd give him more credit than almost anyone of bringing us to that insight, that there's a coherent system of units. Why? Because his discovery of the speed of light being constant, right, really sparked our investigation for all the constants. So what constants are there? I mean, the average person may have very little, if any, interaction or built-up intuition of any of these constants, right? It's very common to feel like they're daunting and confusing, and it's just difficult to start at all. Because maybe the simplest of all would be the speed of light, or familiar. But why would I even call it simple? It's 299,792,458 times 10 to the 8 meters per second. All right, so it's a number that is, as far as the way we go about the world in the sandbox way, it's just big. It's a really big number, and it represents a speed. So it's a very, very, very fast speed. But why would there be a speed limit? That's the point. This constant nature is reporting to us via a number and standardized units that there is a limit to speed in nature. Now, that's not expected, right? As soon as you learn about math and are aware of infinity, then naturally it takes the place of the limit of speed, not a non-infinite number. But we found instead, just like we didn't expect there were limits to the bases, to time and space and charge, mass and temperature, they also connect to form more complicated measures like speed, composed of 2 dimensions now. It's also a limit. Okay, you can't go faster. Can't go faster. What does that mean? How could it possibly be that you can't go faster than something? Okay, this is cool, right? The fact that no one expected that really makes you pay attention to new things about the world. It really makes you want to investigate and have an answer for why. Why is this the limit? Why is there a limit, but specifically this one? Why was that picked out by nature as the limit? And until we have a story, we can't feel comfortable about the fact that this is a parameter fundamentally describing our reality. Right? We currently have a list in physics today of parameters, 44 constants in nature, 17 particle assignments for the fundamental masses in physics. And those represent the best measurements of what we think the ingredients, the building blocks of reality are. All the pieces of fundamental things that you can build everything else from. That's our story in physics right now, right? But we have a pile of those constants. We have the measurements, the string of digits, how well we know them, and so on. What we don't have is an explanation, a story that goes along with what does that mean? Why is it exactly that size? This is really big, but all I'm getting out of this number is that it's really big. Right? I want to get way more out of it than that. And there's a lot more numbers. If you write down all the other ones, the clue is somewhere here in the measurement, right? I should say somewhere here. That's the valuable data that literally gives us the clue. When you compare it to all the other constants in nature, systematically, you can find the pattern. Now, it's given that there is a pattern to find. It's the most beautiful sought-after pattern any humans ever aimed for so far. We all know it's there. Some people try to, be chastising, pretend like they don't know, but everyone who thinks long enough about this knows the fact that we are measuring features of reality, over and over and over. No matter who you are, you will have to measure this. If you're trying to measure it and be honest, that's the number you're going to get. The fact that these properties define reality needs an explanation. It really does. It needs an explanation. It has one, or this wouldn't continually be the same number every time we measure it. There must be an explanation for why it occurs, and the rest of them. And guess where you find the explanation? Not from your parents, not from your teachers, not from your leaders, your political leaders, your religious, it doesn't matter. Nobody has an answer unless it comes from the measurements. The measurements are where the pattern is to be found. Okay, that's the first step. If you're a high schooler and you're excited about trying to make an impact in the world by understanding it well first, this is where you would start. This is what we claim the world's composed of. And if you come into possession of a story of those ingredients, guess what you can start doing with them? There's lots we can do. So this has been the ultimate goal for our replication and for everything else in physics. We want a theory of everything, which means very specifically, we currently have a list of data points, of measurements that describe our measurements for the ultimate ingredients of our reality to the best we currently understand. We want a story. Best would be a single story that explains them, that tells us what they are, that instead of making us look at them this way as a string of digits, which doesn't mean anything to any of us, we look at them in a way that does mean something to us. It still says this, confirms this, but look at them in a way that we can pierce. Because, I don't know, maybe you can, but when I stare at the string of digits, that doesn't mean anything to me. Okay. So, the constants of nature is the pattern we want to explore. We want to find the pattern in the constants of nature, and we have now already come up with a method that allows us to do that. We found that the entire structure is talking about a two-part balance on the outside. That four-dimensional hyperbolic space-time that Einstein was keying us into is bounded by a two-dimensional bound and another two-dimensional bound. One of them is much larger than the other. Okay, that's where the four dimensions come from. The big piece has a primary action, P for primary in this case, and a primary set of boundaries. So the balance is always made from intersection between the big and the small, and the primary with the big one. Okay, the one plus or minus some terminal action for the small one, and there's not a variable option for the terminal boundaries. It's always the same ones inside this system. It's where the system inverts on itself to begin with. So every constant of nature now, using this one prescription, using this one assumption that the constants of nature are being applied to a system that's two-part. Okay, it's binomial. It's made up of two different kinds of things. And one of those things is much, much, much smaller than the other, because this number is 1 times 10 to the negative 7, but it still plays a role. And all of them have just this two-part structure. Now, where does this boundary come from? What does that symbol even mean? It's the symbol we use maybe for field in Chinese, so field theory, for the construction of our external field. And it's equal to the Planck length times the Planck mass over the Planck charge squared. Okay, so using this one prescription, this one assumption that every constant of nature is applied, is speaking about a system under balance, and that balance is two-part under this construction. To solve for the very specific constant of nature now, we just need to resolve these three numbers. We just need to somehow translate this constant, this string of digits, and resolve these three numbers. And I'm claiming that we can do that now using this prescription for every single constant of nature. Where did I get this one from? By noticing that the claim was only right. No matter what number I would pick, it was around 7 significant digits. Even if I switched to a whole different constant nature and started over, no matter what numbers I would pick, around 7 significant digits, we'd always get some error. And as I checked every constant in nature, of course, I found that there was one constant in nature, this one that arranges these three, that equals the size of where the error always shows up. So that takes a long time to get an intuition of where the error is showing up, right? But I knew it was always around digit 7. I'm not getting error around digit 2. I'd always get out around digit 7, sometimes 9, sometimes 4, but it was always clustering around 7. And the fact that one of these guys marked the same place where the clustering was my hint for, well, what if there's an inversion from their own boundaries? With their own boundaries being used to invert things, and I have to worry about the two parts that's balanced against itself. This one I wholeheartedly believe is our symmetry boundary for a few reasons now. That not only does it work for all the constants of nature, but it's also the bound that the zeta function is symmetric on. This is how it self-closes. Remember that the zeta of x minus zeta of 0 equals x times the first prime of the zeta function at 0, exactly when x equals our terminal boundaries. So this is an incredibly symmetric location. It's also incredibly symmetric in the torus sense. So this structure here, LP is made up of the first rotation, and MP is made up of the third rotation. QP is made up of the second rotation. So I can set 2 here. This, in just the rotations, take the scalenes off of them, just take the rotations and put them together, it'd be this over this, or I can compare them and show this one times this one equals this one times this one. How does that have anything to do with a Clifford torus? The generalized equation for Clifford tori, for all of them, is this. x1 times x2, these are two different dimensions, is equal to x3 times x4. If you pick a value for x and you want to be building the Clifford torus, and you pick a value for x2, well, you're fixing more and more what x3 and x4 have to be, okay? We have a caveat that we're very specifically the asymmetric Clifford torus. So we're not going to be one where all four are equal to each other, so we know that the scaling is going to be one side would be bigger than the other. So this is called a square symmetry. Why? Because we have one thing equal to another thing, like one side equal to another side, right? Square symmetry. And it's the Clifford torus general arrangement. Any set of x's that you could put in here that satisfy the equation represents a Clifford torus. Now, out of all the possible ones, there's one among all the possible asymmetric Clifford tori. There's only one that has another square symmetry in it. All of them have this square symmetry. They start with that, okay? But then there's one place out of all the Clifford tori where over here another square symmetry occurs, where you have two things equal to each other, right? Same length. So the maximally square symmetric Clifford torus out of all available Clifford torus is also bounding the exact same place. So it looks like we have a shape now that we can blame on the action of the zeta function at its balance point. That's really a beautiful statement, if it's true. This is my conjecture at this point, right? So employing this one bipartition structure, this binomial rule, okay, this universal binomial factorization rule. It's like binomial theorem from calculus, okay, but we're using the scaling parameter in it. There's two properties, one's always smaller than the other, and all we have to do is search for these three answers to decode every constant of nature, right? Now, it might take a while to search for each bit, but it's not an infinite amount of time, it's not an infinite amount of work. You can do this individually, and as you go, you're searching how. You put in this number with the power, right, the whole scale and everything, into Wolfram alpha, for example, and then you set it equal to these two things first. We're going to ignore this because we know this piece is so small, we'll treat this as 0 for now, or not a non-contributor. So the first step is just to solve the first half. The primary boundaries are the easy part. You can basically just write them down and then solve for that action. So in this case of the speed of light, we would write in Wolfram alpha 2.9979245 times 10 to the 8 equals x, the thing we're trying to solve for. You can call it whatever you want. And then our primary boundaries, in this case, are going to be meters over seconds. And meters over seconds converted to the Planck limits is, meters is length, so Planck length, and seconds is Planck time. So that's our primary boundaries, easy. Now we have to solve for this. We're ignoring the right-hand side right now. We know our answer we're gonna get, it's only gonna be right roughly around 7 significant digits, but we don't care because we want to get that part first and then solve for the other part. All right, so solve for x. Get a number for x. Know that number is within 7 significant digits, right? In this case, you'll get x equals 1.0000000, and then at some point here, some numbers. I don't know what numbers, but you're going to get that for the first 7 significant digits, x is approximately 1. Great, so our primary action in this case is just 1. We can kind of just erase it and solve now back for the terminal action, right? That's just how we piece all these things together. However, I missed the most important time-consuming step, that when we ask each question, well, in this case, when you solve for 1, you pretty much knew you were done, but you want to run through the gauntlet. That's what I call it. Each question you ask, you have to ask it, and you have to pull out every number that the repository you're asking doesn't know about, so that you've asked the question fully, right? If it doesn't know about a certain parameter, you ask it with that parameter pulled out, right? And pulled out squared, and then cubed and forth, just to check all of them. So one of the next projects actually for me and for Avi in Israel working on it with me, we're going to systematize this process. Literally, we're going to try to get a script written that will go and scrub every query we ask Wolfram Alpha, and it'll spit out all the possible solutions. And then we'll set the rules of simplicity and complexity, and the error bars of every measurement will then eliminate which solutions aren't suggestions, right? We'll get a really systematic, fast way to ask these questions and have it then spit out, here's your multiple choice ranked for our best guesses already. You know, the best sigmas at top and down as you go. So then you have a way of looking into the world that doesn't tell you what's going on. It tells you, well, here's compatible options for what you were looking for. Now, by using, in a very, very rich way, systemization, okay? Now, it never tells you you're right. No matter what perspective you have, you never know that you're right. So you keep going. How do you do that with this? First of all, you try to make sure that every question, well, once it's systematized or automatized, then it will be much more confident that you've done them all and didn't miss them, right? Second, you keep track of all the good possible answers. You don't discard them all out of hand. You take your best one, you try to take it seriously, you try to understand what it would mean and develop intuition around it, but keep the other ones in case that one wasn't the right answer. And you do it for every single one. For every clue we have about what the fundamental structure of reality is, for every constant in nature. And with that list, you then have an outstanding, overwhelming similarities that will show up if you're on to the truth. There's going to be a pattern or story that develops. And you're getting to the story by how? By asking further questions, by using the powerful modern tools of systemization and Wolfram Alpha to use the libraries of what things are out there to be able to find what works as an answer. That never means you found the answer, but it's the best way to go. Start with, what are the possibilities that satisfy the actual constraints I believe in? Okay, so that process with this beautiful hint that the world we're talking about is talking about characteristics always balanced under a two-part system. Asymmetric in size, this is much smaller than that, but it's always a two-part system. So it gives you a way to individually now make progress. But then we can also have a step of comparison that gives us insight about what all these things are saying together. Great, that's where the step of real confidence comes, when you get an insight about what the speed of light is actually saying geometrically. And that insight tells you something that then is confirmed by another story and another concept of nature. Now things start to coalesce, but you also start to know what to look for now. You start to know what new questions to ask, and you know where to look for things, and you start finding more things. So it kind of snowballs. It takes a little while to get into it, just like writing, right? It takes a lot of work to be systematic enough for you to employ richly the powers of writing or literature. But using the tools, the modern tools of mathematics, same sort of thing. You benefit from all the time you spend on it, but it does take a lot of time. And in this case, if you spend the time on this quest, on this puzzle, anything that you find that advances us, brings us one step closer to being at the state where we have universal replicators, to be at the state where we're no longer dependent on resources, and to be at the state, therefore, where we can get back to the major project of evolving our own consciousness. I think that would really be a beautiful world to be in. Okay, so here we have a geometric picture pulling up here. We have a coalescence between the rules of Clifford Tori, which, by the way, are richly connected to all algebraic geometry and so on. Okay, a lot of stuff coming in with the way we're saying our picture is fit together. And the fact that the zeta function itself is closed symmetrically at that one boundary is a very powerful hint that the story so far is coming together. A lot of things are falling in, but I recently went through and did this process again, very systematically, writing down by hand every single entry and every power option and crossing them off as I go and keeping track, and it took me several notebooks. I finally knew with confidence what I'm doing is systematically comparing them all. And what do I have to do to do that? I have to process every constant of nature through this prescription only and be scientific about how I report the possible answers, right? Now, how is it scientific to discard any of them? Well, we're looking for answers that can give us story, answers that can give us some bit of information about what's going on, a geometric piece of information, something that we can turn to story. And if you see an answer that you can get to that constructible number by this set of crazy things, and there's 14 things added together and some divided and constant you never heard of before, it doesn't mean it's wrong. It means it's impenetrable. It's not something you're going to make story from. So for that reason, you can discard it. What we're looking for is a simple representation available using any geometric notion that can get you to where that number is. Okay, that's what we're looking for. And you don't, this is a really beautiful step, you don't need to know what the answer means to get it, to have it in possession, to make your multiple choice list of answers. You don't have to understand any of the answers at first to find them with this method. Then what do? You have target things to figure out. You ask this to the Planck's constant. You've always wanted to know what's up with Planck's constant. Use this prescription to decode Planck's constant. You'll get a list of possible answers. You can sort them using the sigmas, mean based off the error bars of the measurement for Planck's constant. And then you'll have a confidence interval. What options could possibly be the answer? And when you have those options, let's say there's 4 good options that you couldn't narrow down but less than that, you take every single one in turn seriously. Say, all right, today I'm going to think of that. The first one, that's the answer. Now, what's that constant mean? Look things up all day on it. Try to get every bit of information you can out about the first answer until you've exhausted it, everything you can do. Then go to the next. Take them seriously at least once for a whole day and see where it takes you. If it doesn't go far enough, move to the next one. You don't have to take things seriously forever, but you should take ideas seriously the first time, just to let them be in you, right? Then you can disagree with them, you can reject them or whatever, but if you're discarding them as they're coming in, you're fighting against your own evolution. Okay. Our goal now at this point is to, one, systematically automatize the process so that we confirm whether what I did it can be improved on or not, okay? But also so everyone else can watch the steps and it'll take way less time from it. So more people can be involved, the easier we make the threshold for that. Also, that'll hopefully help evolve and clarify details of the story, but we've done this to a point already where we have answers for every constant of nature. We've transcribed every constant through this prescription and found a simple representation every time just using the Planck constants as its dimensional representations. So using the boundaries of the dimensions themselves as the things we're intersecting, like this divided by that, okay? We find a simple primary action almost every time. It's either 1, pi, or J1, or powers, like 2 pi or J1 squared or something. Those are the 3 most common things that show up in this one out of all 44 constants of nature. Beautiful. The terminal action is involved with some other J and some geometric action, right? Some partition action and some geometric, say, rotations, so like 2 pi times the real part of J3. That'd be an example.
Well, it's interesting you say that, just because even built into Planck's constant is 2 pi. Mm-hmm. That's very interesting.
It is. All these constants have geometric representations. That's what we're after. We have partial geometric stories of some of them at the, in their applications. But what we want is what's holding them in this character. what's responsible for that action. And when we have that answer, what we think is going to come is not just, oh, great, we can now predict the magnitude of this behavior, of this function, and then try to take advantage of it. We should know also what it's connected to orthogonally. Meaning, when you disrupt this part of the action, these things will automatically be disrupted too. So the level of integration or understanding should go up immensely when we have this internal picture. The clues that we've gotten from all these concepts of nature, from plugging them in, have now led to a story that goes like this. The domain we are talking about when we talk about physics, the fundamental domain of how things manifest with their properties, is actually characterized by the smallest possible minimum volume complement. Okay, the hyperbolic figure 8 knot, or the double cover of the Giesking manifold. This is easily thought of as, imagine you're in an infinite void that's supporting waves. Okay, there's a whole bunch of big, small, all different sizes of waves undulating through this void, but they're just carrying through and scattering off each other. It's just random noise. Now, this collection of random noise sometimes can produce places that do things together and some things that tear apart and so on. Eventually, you could get a collection of waves that just coalesce together in a way that then wraps back on themselves, that forms a manifold action. Now, there's an infinite number of manifold actions you could achieve under wave action. The question is, what's the smallest one? What's the easiest way, the minimal way in which you can wrap things around such that when you do, they would continue to wrap around and always do that same thing. Now notice, when you form this, what do? You're inventing a new situation in this infinite void. You're forming a region in the infinite void, a finite region that's now under a characteristic balance. Everything in that region agrees with the dynamic rules there. Outside the region, those dynamic rules don't apply. They're not even there. They're there because of how this region itself is integrated and continuing to integrate itself, to differentiate and integrate, right? They maintain that flow, that action all the time. And it's a complex action, and it changes as you go in from scale to scale, but it's still just a fixed, finite action. Okay. That's the story. What are all the constants in nature? Or what's the outside? The inside is the hyperbolic figure 8 knot, the minimum possible complement. And the outside projection of that, literally the external balance parts, 32 total pieces, define the n hypersphere of maximal volume, the largest possible constructible form there is in geometry. Now, to be really clear, I'm not saying that you couldn't imagine in your head a sphere with a bigger radius than that. I'm saying that in geometry, we've discovered there's a form that's the maximal constructible form, okay? The maximal logically built geometry, and it's the n hypersphere of maximal volume. If you try to make a hypersphere in greater dimensions than the hypersphere of maximal volume is in, it decreases its volume. It doesn't keep going up. You go up in dimensions, it goes down. That's why there's a maximum. At first, when you go up, the volume goes up, and then at some point, it maximizes, and now keep going up in dimension, your volume goes down. That maximum one is balanced literally as the inversion of the minimal volume complement called the hyperbolic figure 8 knot. And how do we get to resolve its properties? Well, we take the equation for the hyperbolic figure 8 knot. This is how we write down, one of the ways we can write down the equation for the volume complement of the hyperbolic figure 8 knot. I, the square root of -1, times by a dilogarithm of 1 over the imaginary golden ratio. I equals -1 to the 1/2. And the imaginary golden ratio equals -1 to the 1/3. Minus a dilogarithm of the imaginary golden ratio instead of 1 over it. This equation for the hyperbolic figure 8 knot, this gives us our dilogarithmic structure, our argument, the imaginary golden ratio that everything is dividing on. And if we want to see what are all the other pieces in play look like, not just the part that wraps back on itself, we get there by taking all the possible signs of this arrangement. That's all. There's 5 sign places, and there's 2 possible signs each. So 2 to the 5 equals 32. These are the 32 strips or pieces that are connected together to define the n hypersphere of maximal volume, literally containing within it, in its most internal part, the hyperbolic figure 8 knot. Okay? So to go from having just the hyperbolic figure 8 knot to having what its outside pieces are, we just write the same equation down a total of 32 times, and each time we take out one of the different iterations of plus and minus. There's 32 possible combinations of plus and minus, then we've got them all. Then what do? Plug each one into Wolfram alpha, ask what it equals. This one equals the hyperbolic figure 8 knot. What do the other ones equal? I'll leave that maybe as an exercise for people to do, but that's not so difficult. Literally type it in like this. Yeah, I wrote that down for you so you can type that in easier that way. The imaginary golden ratio is not on Wolfram alpha yet, so you might have to write it like this. But same thing.
Last night that they didn't necessarily have the imaginary golden ratio, but they did have some of the logarithms, and I think they had like -1 to like the -2/3 or something like that.
Yeah. You can rewrite that the same thing. If you write that in -1 1/3 way, then we're saying this. I times by the logarithm of -1 to the 1/3, but over that, so it's -1 to the -1/3, right? And then minus logarithm of -1 to the 1/3. And then you can turn one of those, if you divide 1/3 of the circle, this 1/3 division implies also -2/3, right? So we can turn a 1/3 into a -2/3. And when you see it that way, you're saying, oh, I see the 1/3, 2/3 split division of charge, actually.
It should be combinatorically equivalent.
Yeah, it is. It's exactly equivalent, yeah. So I think this is the most beautiful way to write it. It's short and concise, but it also helps you see that the imaginary golden ratio is a very intrinsic and central argument. Now, what else does imaginary golden ratio central and intrinsic to? The gamma function. And to get there, let's start here first. If we take gamma of x plus 1 and set it equal to gamma of x minus 1 and ask, is there any place where this is true? Is there any x that solves this relationship that would be unitarily balanced in the gamma function? And it turns out the answer is x equals the golden ratio and -1 over the golden ratio. Okay, now what if we wanted an inversion to this? Well, now if we instead say, let's set the gamma function of x plus 1 equal to the negative of the gamma function of x minus 1, and ask now, solve for x. Now the solution is when x equals the imaginary golden ratio and 1 over the imaginary golden ratio. So both both golden ratio and the imaginary golden ratio are built intrinsically in the unitary fashion into the gamma function. Okay? And the imaginary golden ratio is the argument, the base argument of the balance creating this dilogarithmic integrated structure we call the hyperbolic figure 8 knot. Beautiful.
What the heck, man? It's just, it's crazy, man. It's crazy beautiful.
It's all kind of crazy because we're used to thinking of the world as this in-place magic thing that the globe moves around through and the sun's in the center of and so on, but the presence of it to begin with was magical. Here we're starting from conceive the world as empty at first, meaning the universe is empty, there's nothing in it, and it's just an infinite void. We're going to ask, how do you make the smallest possible consistent universe? Meaning once you do it, if you step back away from it and let it keep going, it'll stay. I want the boundary conditions to be self-reinforcing, to be self-making, to not require always an input from somewhere else. Great. The smallest possible condition for that literally is defined in geometry as the Giesecke constant. And now, from the investigation I've made by looking into the constants in nature, I'm now interpreting it to say this. that the Giesking constant, the smallest manifold, when you achieve it, you achieve something that's wrapping back around itself that defines the time field, the 0th base, okay? That's the time field. But when you do that, all these things outside are doing something in response because you keep doing this to them on the inside, okay? So all the external, the rest of 32 pieces, okay, they're all counteracting to the presence of the hyperbolic figure 8 knot in the beginning, inside them. They can't cross the boundaries, or at any point in the fluid outside couldn't ever end up inside, and vice versa, but their structure is made by it, right? They're held up by each other, just like hurricane walls are held up by both sides. Our goal, of course, to restate it as much as possible, is to get to a point where we can manipulate and design a computer that will do these exact sets of manipulations, that will do exchanges along only the constants of nature for the transforms we want. We don't want a lot of friction and noise and other stuff to be involved. We want to be able to take advantage of exactly those boundaries. And why? How can we know ahead of time that that's what we want to use? Because we know nature's using them. So if we can, then we should be able to make everything that nature's already made, or anything that we've currently been able to see or take advantage of. Yeah. That's the goal. What steps are needed between now and then? We have to write the program. To write the program, we have to have a library that's as simple as possible, meaning it's composed of the smallest number of ingredients possible and no less. And what that number is, who knows? We have a system here where we have 5 magical boundaries, not magical once we put them all together and reveal them. We start out with 5 unexplained boundaries, the Planck constants. In our picture, by revealing what they are, they're composed, or they define 5 different ways of deranging that minimal system, right? They are literally the actions that are decomposing it, tearing it up at different scales, and twisting it all together. How the whole system, both inside and outside, is acting is defined by 5 different bases that coalesce together, or conspire to dance together just right. So we need to be as clear as possible what's going on, but we need to eventually have the transform logic. That's what we're actually ultimately after. So when we have the logic for how they all fit together, the reason we want that logic for how do these things all fit together, because it'd be immediately obvious with that closed, if they all fit perfectly, it should be immediately obvious how the transforms that are allowed are allowed. What can we do from this state to that state? What are the options? Because when you have the connected boundaries, they literally define the transforms that would allow stability under action. Okay, so that's our goal. Right now, where are we at with that goal? Well, we have our 5 Planck constants, and those 5 boundaries are able to, when we plug them into our prescription for the constants of nature, to decode, therefore, to constructively give us the values of the constants of nature just with them. Just with those 5 boundaries, and what else do we need? We need some geometric constants like pi, and the universal parabolic constant, and Euler-Mascheroni constant, and the golden ratio, and some things like that. But these are all geometric stories already, which is wonderful. The fact that we needed these geometric characters to tell our story gives us our next clue. Find all the things related to the golden ratio and say, oh, whoa, golden ratio is built into the gamma function. I'm now interested in the gamma function, and it snowballs from there. So all these little clues are amazing, but our library right now consists of what? 5 constants for the Planck constants, okay? Then we have our j's, which are 6 different values for the j's. And we have pi, pup, the golden ratio, the imaginary golden ratio, maybe 4 or 5 more geometric constants. And from that small list of library, we build all the constants in nature and all the mass particles and step up from there. So our library right now is extremely small. It's got 6 j's in it, and it's got 5 boundaries in it. And from that, everything else is formed. So I love the simplicity of that. Now, does it make it right? No. I'm never going to try to take that stance. It doesn't matter if I think I'm right. What matters is if it can be turned into a machine that replicates. So we keep going until we get a coherent story that allows us to accurately and repetitiously, over and over, reliably transform the things we want to. Cool. When we're trying to figure out what's going on visually, the big quest is, how do the pieces of the exterior domain fit together? And there's one equation that answers that question. if we write down the equation for just a hyperbola, here we go, a general hyperbola. Set it equal to anything you want, plot it, but I want to modify my hyperbola just a little bit to make it so it's self-closed. So I want the volume element, the cubed element, to be divided by a circle over and over and over. And I want this construction, this is coding a relationship built into the way things fit together on the outside. So I want this construction to be equal to just 2 rotations inside the limiting partition boundary, which in this case is the plane mass boundary. Okay, so this one equation, just like we had one prescription for a universal binomial factorization that we apply to every single constant in nature, here we have one balance maintaining the construction of the outside. Everybody, all the constants in nature will agree with this balance. Okay, now this equation can be solved to have solutions, and it doesn't have just one solution, and it turns out it has 4 solutions. So let's draw them. This one's real close to 0. We'll call it Je1. And this one's out here on the line, on the real line. We'll call it Je2. And this one's out here, Je3, and symmetrically reflected across it is going to be Je4. All right, these are our partition solutions of this connection. So if things are bound under this prescription, then that means that these 4 partitions are fixed into the way everything's moving about from then on. Okay, why do we care? Well, these partition solutions literally give us the solutions to every constant of nature. Like I said before, all the constants of nature will agree to this fitting of things. So the solutions here will play a role in every connection that we're defining as a constant of nature. There's going to be something of them playing a role. So here's the algebraic geometric connection we care about here. When we take all of our partition constants and ask, what's their sum? Well, the most useful sum would usually be the balance, 0. And in this case, of course, you can see pictorially that's kind of true. If we add them all together, we get 0. If instead of taking their sum, so instead of adding all the solutions together, we take their product, now we're just multiplying them together, and we get 2 pi. If instead of the sum or the product, we want to take their quadrants, then we just take the square of each and add them together. Or we could take the negative of that all the way through. Either one counts as quadrants according to the definition. I'll write it this way, Je1 squared, Je2 squared, 3 squared, and that equals negative 4 pi. If I made them all negative, it would be positive 4 pi, so it's both. It's both negative 4 pi and positive 4 pi for the quadrants. Of what? Of these partitions in this arrangement. Okay, so we're dividing up under a 4-dimensional connection, a sphere. We've got a product, we're producing a circle, and we're maintaining a balance, simply. This is a beautiful algebraic geometric connection. Why? Because it transcribes what the zeros do in collection. Okay, now, where do we want to go next? There's a lot of symmetries built in here that you could write down algebraically as properties being maintained, and I encourage that exercise. It's pretty easy and simple, but when we get down to the most complex combination, the 4th power of, actually, side note now for a second, there's another way I can list these. So I can write them all down, Je1 with some numbers, 0.085, Je2, 3.6 something, and Je3, it has a number and a imaginary part times I. Okay, and Je4 has the same number here, because their real part it's a negative number, is the same for both of them, but it has a negative amount, same number here for I. Okay, so these two numbers will be the same, these two numbers will be the same. They're both negative, this is positive, that's negative. So 3 and 4 have X and Y components. They have real and imaginary components, okay? 2 parts to them. Now I can talk about this Je3 and Je4 position another way. I could talk about arrow down here to J4 and take this length as J_R, the radius from the center. It's not from J1, it's from the center. Okay, or I could have done it here. Same thing, that's also J_R. This is J theta, and this is negative J theta. So I can get to J3 or J4 using the real and imaginary parts or the radius and the angle. Okay, there's just two ways of getting it. But that means I have also J_R and J theta as descriptors of this connection. Great. Here's a really fun connection to notice. If you're interested in understanding quaternion connections, then we can start with, algebraically, just one of the prescriptions for quaternion algebra. So you can verify by factoring out yourself that A times C minus B times D squared plus A times D plus B times C squared equals A squared plus B squared times C squared plus D squared. So this is a quaternion true statement. It's four-dimensional connection. ABCD has four parameters that are being connected under the quaternion balance. Okay, that's all it says. It shouldn't feel like it's too profound. It might be complicated a while since you've done factoring, but if you take the time to go step by step and factor out the left side, you'll see that it equals to the factoring of the right-hand side. It's just a simply true statement. Well, there are like 24 ways you can rewrite a quaternion algebraic statement that's true. And if you have any of them, then you actually have a what? A quaternion balanced metric or system. Okay? So we're interested in wondering, can we make sense of quaternion structure from our connection? Why? Why would that be a natural connection? Well, we believe that our world is, the external world is under a projection balance of 4 dimensions, right? And quaternion algebra is 4-dimensional. So it'd be really nice to have a more rich intuition of what the structure of quaternion algebra is doing on every level. If this structure maps to quaternion algebra, then this geometry gives us that intuition. So let's check. Is there any set of these parameters that we could use to put in as A, B, C, and D in order for this to still hold? Like, you could put A, B, C, D, any number you want, you pick them randomly, but it wouldn't work. You have to pick the right numbers, A, B, C, D, for this structure to work, right? Turns out if you set A equal to the real part of J3 and B equal to the imaginary part of J3 and C equal to the real part of J4, D equal to the imaginary part of J4, and plug them into the equation, and then use all the symmetry relations that you can write down, true statements about these things, you can then find that this statement is still true, and it's also equal to J_R to the 4th. When you plug all those in there, they hold this quaternion arrangement when they're equal to J_R to the 4th. And you don't have to use just this prescription. I could have started with A equals the imaginary part of J3, and B equals the real part of J3, and so on. There's 4 different ways you could rearrange these just to get the exact same answer. Now, I'm not just saying that there's 4 different prescriptions that when you plug them in satisfy the quaternion algebra. I'm saying that all 4 of those also equal J_R to the 4th. So we supersymmetrically satisfy the quaternion connection with our division parameters in 4 ways. Next clue. Hopefully it's enough for you to be interested to keep looking further, right? Anyway, that's a big deal. Quaternion algebra is not such an easy thing to understand. I mean, if you only interface with it algebraically, then you can get really good and fast at factoring, but the intuition for what you're doing physics-wise is almost completely separated, right? Here we're kind of noticing that we can bridge our algebra with our geometry. We want our algebraic geometric connection. We want to know how do we transcribe the connections that happen in the world between an algebra and a geometric picture. So we have a story, we're saying one connection equation for the exterior domain, provides exactly 6 partition constants, and with only those partition constants and the 5 Planck boundaries, we were able to prescribe everything on the poster, everything that's a fundamental measurement needing explanation in fundamental physics. All the constants in nature and all the particle masses, the whole particle zoo, are perfectly mapped with just those and a handful of small constants, geometric constants like pi, the universal parabolic constant, or the Mascheroni constant, the golden ratio, the imaginary golden ratio, and stuff like that. The most beautiful central operators in our current geometric models as it stands. We got all of our j's in one connection, the hyperbolic vortex equation, right? That's literally just describing 2 things, the hyperbolic connection, but also the way that it breaks up inside of its last partition boundary. Fantastic. And those connections literally litter the explanations of the constants of nature. The right-hand side is always some sort of 2 pi times one of these j's, one of the pieces of these partitionings, or 1 over 2 pi, or some geometric, easy to understand constant multiplied by 1 partition parameter. And how do you interpret that? In this partition direction, the partitioning looks like whatever the geometric thing is. If it's a 2 pi, then in that direction you're doing a circle as the partitioning. If it's not, then you're doing whatever it is. But yeah, so it gets a lot easier to try to read the algebra, or read the geometric story from the algebra.
What's J1 squared?
Good question. In physics, one of the clues hardest to ignore is called the fine structure constant. So it's got this symbol, just like that, okay? It's a dimensionless constant, and it's got a lot of lore around it. Why? Because it's a dimensionless constant, kind of like pi. It's telling us something about the geometry of chemistry or the electron, okay, directly. It's just we don't know what it's telling us. And why do I say that? Pi tells us something about the geometry of, it relates to the geometry of circles, right? This number is another dimensionless number like pi. It has a string of digits, but it doesn't have a measure associated with it. It's not a length or amount of time or amount of charge. It's just a geometry. Interesting. Also, this is just a geometric number with no units, no dimensions attached. So it's a universal thing built in to what? Where do we get this number from?
Just relating other things.
Yeah, from looking at the constants in nature, right? In chemistry, electrons, and so on. This doesn't come from math. This comes from physics. But physicists believe this is a math constant. It's a geometric constant, is what I mean, right? It's dimensionless and geometric. We need its story. So in our case, we have a really beautiful story that tells us what it is. The fine structure constant is equal to J1 squared. Really, really, really beautiful. In fact, we can go another step if you want to know how do I interpret the electron's charge, because we have a charge boundary. If I got comfortable with the fact that there's a charge boundary called the Planck charge, well, now I have to get comfortable with the fact that there's another charged thing called the electron. Oh, it's getting complicated, right? Well, not really. The charge boundary is the source of what we're calling charge. It's the action of charge. But what's the shape? What is it? How is it bound on itself in a balance? It has to be there balanced in a way. So its actual action is just the first partition action. So we take the charge boundary and we partition it in the smallest way. The first partition action applied to the charge boundary literally equals the electron charge. Okay, it's not close, it's exactly, and we know this one very well. The fine structure constant is telling us what? That we have the first partition constant from our hyperbolic vortex equation under square arrangement. The inner constants of nature, this square arrangement of this partitioning plays a role. And it shows up a lot of times like that. In fact, it also shows up to the 4th power. Lots of places where this shows up. If we take the electromagnetic force and we divide it by the strong force, it equals J1 squared. So the relative strengths of these forces are geometrically bound. Remember how we discovered gravity is geometric? Here, chemistry is geometric. Okay, they're geometrically bound, and we can say more than that now. What geometry? Well, they're employing squarely this first partition constant. And that first partition constant being employed, by the way, forces the rest of them to be in play too. You can't get that one by itself. It's a consequence of this balance, which comes in 4 parts. It can't be one part. You don't get one and the others don't come. If you get one, all the rest come, right? That's the coherent explanation of this connection. So, find structure concept now being revealed in a geometric way, the connection between all of this structure, the smallest partition balance in that connection, by the way, right? Yeah, that's utterly profound. I mean, it's utterly exciting. Look, these are things that, what Feynman put it at, every physicist or every good physicist puts this number up on their wall and worries about it, right? You can't really be a good physicist if you're not trying to make sense of things. You got to worry about this one. Why is it you can't get away from this one if you could get away from others? A lot of people get away from worrying about the other ones because they have dimensions on them and they don't have any idea how to get past this coherent system of unit thing. But with the coherent system of unit confusion, you still got this thing slapping you in the face. All right, what about this one? Dimensionless constant needs an answer. It's a geometric parameter of some sort that's telling us what reality is doing, but until you can interpret it like we can interpret pi geometrically, you don't know what's going on.
Well, it's also all over the place.
It's all over the place, yeah. Chemistry depends, obviously. The electron charge is the base of chemistry, right? Moving electrons around is chemistry. So chemistry depends on this structure. Not just Jo1, because they all come together. This is the exchange mode. This is the balance we should be employing. And we know it because all of its partition constants are the ones that solve the balance of the constants of nature. All right, so that's where we're at. We really want to encourage everyone to either work on it by themselves or together. This is about getting somewhere of insight. And whether or not you think we're on to the right story, understand what we're saying to how we got to the story so that you can get to one better or challenge it in the right way. We have a simple library now built from 5 bounds, one for time, space, charge, mass, and temperature. And we have a simple prescription called the universal binomial factorization. Okay, that way treating a big piece and a small piece of decoding every constant of nature. And with just these j's, this is one external balance, the hyperbolic vortex equation, giving us these partition constants as representing this balance. With just those j's and those bounds, we can then decode every single constant in nature, make it a constructible number. That's a good topic to push a little bit on. Constructible numbers. Since all of this requires writing, it all requires systemization, it requires numbers. You can't report to me a measurement unless you've got some systematic way of reporting numbers, right? Then, constructible numbers. What do I mean by that? Norman Wildberger is a fantastic YouTube mathematician that puts out hundreds of videos. And he makes the point that a lot of mathematicians are into what we call real numbers. Okay, meaning they believe that the real number line is infinitely smoothly connected. And he said, we have got no reason to believe that. In fact, it's a bit incoherent to talk about real numbers in many ways. One of the ways is this. There should be only, numbers are only usable in the sense that you can use them. They must be constructible to use. What do I really mean by that? If you start on a number line that's just one-dimensional, we can start at 0 and put 1 out here. But if I were to ask you, how many places on the number line can you get if I've only given you 1? You can reuse 1 as much as you want, but you can only use 1s. You can use addition, subtraction, multiplication, and division, but you can only use 1s to build your world. How many places can you get?
We're talking about just integers?
Sure, you get all the integers, which is an infinite number of places, I guess, right? So you can build 2, 3, 4, and all the negative ones and so on. Good. Then you can probably, now that you got 2 and 3 and 4, now you can do fractions. You can do 1/2, 1/3, and 1/4, and so on. So we can build a lot of places. And if I want to ask you, how many of the points between 0 and 1 can you constructively get to? The answer would be an infinite number, right? Because you can go an infinite number this way and do infinite fractions. Okay, but what?
It wouldn't be all.
But it wouldn't be all of them. Exactly. The total number between 0 and 1, would there be points missed in that infinite set? Mm-hmm. Definitely. Lots of them are missed. You might argue the vast majority are missed.
Segregated.
Yeah.
In ancient Greece, were all obsessed about that.
They really were. They really were. They wanted to be able to get to things that could be achieved via ruler and compass, right? So just by rotating and measuring length to be able to build a construction. So they were very interested in constructions that could be built. There's an infinite number of unique locations between 0 and 1. There's an infinite number of them you would prescribe if you just took the list of 1/2 and 1/3 and 1/4 forever. But even if you did that, let's do it. Let's see. We've got this point and this point and this point. And I missed most of them. You can't get everything, is my point. And he's very on. Norman Wildberg is really making this point in beautiful and funny ways sometimes. Numbers are useful in as much as you could construct them. If it would take you more information than the whole universe to identify that point, what does it mean to us? Nothing, right? It needs to be achievable. So constructible numbers. We're now interested in not just a number field. We want a number field to literally be our balanced mechanism. The field is the region where operations are all true, right? The regions where plus and minus work everywhere, no matter where you start. Plus works for you and minus works for you, and it's invertible. Multiplication and division with some exception points. Like the point 0, division doesn't work. But in the volume, it does, okay? Things like that. We're interested in a system that we can construct only out of minimal pieces. And I see that as exactly what we're doing.